Welcome everyone to one more edition of our algebraic and foliation student seminar at IMPA. Today it's a great pleasure to introduce this mathematical colleague which I could met in Chile some years ago in a mathematical event. So it was so nice that we keep in contact so far. And so Yulieth took two master's degrees in mathematics. She took a first master in Cinestav in Mexico, who is a center for who which is a center for some scientific investigations. She took another master's degree in Université Toulouse Trispo Sabatier in France, and she defended her PhD thesis last week. So now we have a fresh PhD, a fresh doctor, and she defended in the Università di Bologna in Italy, and now she is invited scientist and the Riemann Center for Geometry and Physics and the Leibniz Universität Hanover, and she is supported by a Riemann Fellowship. So, Yulieth, it's a great pleasure to have you in our seminar. So, feel free.
Ok, muito obrigada. É um prazer para mim apresentar este seminário. Desejo um dia ter a oportunidade de visitar o Brasil e participar de outros seminários. Dançando lambada, da lambada me faz delirar. So thank you very much for the invitation. So yes, in this occasion, I would like to discuss one of the problems that I was interested in my PhD that was relating to study some particular automorphisms. These automorphisms are very known because produce a lot of examples of K3 surfaces, and also many of these properties can be reflecting also in higher dimensional of K3 surfaces, which are known as irreducible holomorphic symplectic manifolds. And but here since Eduardo told me that this is a seminar for students, I would like to present more or less what is the main idea of these constructions, and then just to mention a couple of results that were in collaboration with a professor in Milan, and we tried just some particular cases. So we will see in the along the talk that there are some facts that are very known, but other cases no. Okay, so let's see that it works. Okay, perfect. So where are the surfaces that I'm interested in? So the surfaces with trivial canonical bundle. So it reminds that surfaces here are compact. Okay, they are also complex. So we are looking in complex numbers. We consider also varieties, of course, of dimension 2. Okay, and the fact that is trivial, the canonical line bundle is trivial, we will say that that this is allomorphic to the trivial one. So we know that these surfaces are classified and basically are K3 surfaces or two-dimensional torus. Okay, so how can I distinguish between the two K3 surfaces that have trivial canonical bundle? So basically, so this is an invariant that depends of these holomorphic two forms. So here, if you ask for the dimensions on one forms, we get this number that basically is the dimension of the global sections on one force, yeah. And if this number is different to 0, then we get the case of two-dimensional torus. And in the case that this number is 0, we get that the classical examples of K3 surfaces. Moreover, this number is also relating to the question that it is simple connected or not. And the first one is are simply connected, and the second one is clearly that not. Okay, so examples of K3 surfaces. So the first one is the baby example. Okay, so the baby example is the quartic, the smooth quartic in P3. So let's consider, so for example, this one, right? And this is in the, considering P3, you can prove that this is an K3 surface. And then you can prove that it's simply connected. This is an easy exercise. I mean, in topology, you can consider, or also you can consider the Lonisz sequence by the exponential sequence, and then you prove that the global sections of the one-fourth of this X, it's in the global section of P3, and then there are no sections there. So in particular, there are no 1, 0 sections on the for X. So also if you want to prove that the canonical bundle is trivial, then you use the adjunction formula. And actually, this is also an exercise true for any section on the of degree 4 in P3. And then you prove that consider the adjunction formula that the canonical line bundle of X is also trivial, right? Since the canonical bundle of P3 is O minus 4. So this is an example, the baby one. And the second one is relating to a classical example of surfaces that is called the Kummer. So what is a Kummer? So you start with an abelian. Okay, you can see. Okay, yes. You start with a two-dimensional torus that I denoted A. And then you have this involution. You always have this involution in the torus, which is taking A and sending to minus A. And then if you consider this involution, you can prove actually that there exists 16 fixed points, right? So when you consider these fixed points by the involution, this map, which is the quotient map, the natural quotient map, in the equation here, it's seeing its fixed point for the involution. It's a singularity. Okay, and the singularity also we know which kind of singularity is. It's an A1 singularity. Okay, so if you want to resolve this singularity, you know how do you resolve it, because it's a type of ADE, and moreover, the minimal resolution that is given by a sequence of blow-ups of these isolated points give you a new surfaces here, which is now non-singular, and actually introduce -2 curves for each singularity. So in total, I will have 16 singularities, right? So let me just to say that A here has 16 fixed points, okay? And let's denote it by Pi, and Q the Pi, it's now a singularity of A1 type. When I resolve the singularity, I introduce in cum A, then I introduce an exceptional curve, right? And actually, this curve is a minus curve in cum A. So there is a set of -2 for each point in the singularity, right? And actually the picture that I show here it's a singular K3 surface. So I mean, it's in the quotient here, and if you can see, if you count here, I mean, this is an three-dimensional model. Okay, essentially you are counting for these 1, 2, 3, and 4, and there are 4 of this type. So in total you have 16 singularities. So this is more or less the picture of what is supposed that is the picture on the quotient. And then so I'm interested on this new K3 surface. Okay, and these K3 surfaces actually are relating to my first torus. So this is at the level of the hot structures. Actually, these say that the transcendental part we will introduce later the good notions, but at the level of the transcendental part, these there exists a hot isometry between the transcendental of the Kummer and the 2 times of the transcendental of A. All right, so this is some invariants which are coming from this classical example. Okay, and we will try to reproduce these examples for other orders. Okay, so what is the question here? So suppose that you have a K3 surface. Okay, and you want to know if this K3 surfaces is the Kummer surface on some complex torus. So this is equivalent to say that there exists a torus such that the quotient by the natural involution is birational to this K3 surface. And in order to do this, to present the story about how to answer these kind of questions, we have to introduce some notions on lattices. So I mean, I will introduce what is a lattice here. So a lattice L, and actually with a bilinear form. So what is this? So this is an zeta model of finite rank. Okay, and we will say that this is a map from the product of L in zeta, and then with this is a non-degenerate bilinear form. And in particular, if we consider, we will say that is even if for all in L, this number is an even number. And moreover, we will say that L is unimodular if L is, when you consider the equation by the dual and L, this is trivial. Okay, so this is yes, trivial. Okay, so this is also equivalent to say that the lattice is isomorphic to the dual lattice, but the dual lattice actually unseen like as a Q vector space. So it's kind of, but okay. So this is the discriminant group, so which is an important invariant. And also the bilinear form on L induce an bilinear form also in the discriminant group, but now the coefficients are different because now AL, I mean this bilinear form that I want to associate to the discriminant group have image in key module Z. Okay, so also another notion that we need to introduce is primitive embeddings. And then we will take, if we consider L and M two lattices, and we have a map. Oh dear. Sorry. And we have a map here, like this one. then we will say that is primitive if the quotient is free torsion. Okay. So what is why the link between the lattices? Because we have Torelli theorem, and Torelli theorem is also very useful in order to distinguish K3 surfaces. So an example of a lattice is that, so the first example useful in this theory is the cohomology group. Okay, so here, so let me just I will do that at a night page. Okay, so here examples of lattices are the cohomology group, okay, with the cap product. Okay, this is a lattice, and moreover, if we have that X is a K3 surface, this lattice is always the same. So for any K3 surfaces, this is isometric to some abstract lattice, which is given by 3 copies of the hyperbolic plane plus 2 copies of E8. Okay. So this is something that comes so related also the structure. Now for K3 surfaces, it's an topological invariant, so it's the same. But if I want to distinguish 2 K3 surfaces, I need to distinguish as the complex structure, right? So how do you see this in the cohomology group? You can consider the Néron-Severi group of X, which for K3 surfaces is the intersection of this one with the second cohomology group. Okay. So in particular, this number is so the rank of this Néron-Severi group, which we denoted by rho, is something between 1 and 20. Okay, and now if you want to distinguish between 2 K3 surfaces, the important part here is the Néron-Severi. Okay, and we will see actually that the Néron-Severi contains this information of these curves introducing in many of the times for resolve these quotients. Okay, so there are some questions at the moment, or
I think
no?
no, Yulieth, you can go on.
Okay. Okay, so this is a lattice. So this is the Néron-Severi lattice that I'm very interested. Okay, and the first person who tried to resolve this kind of questions of when a K3 surface is a Kummer or not was at the level of lattices was by Nikuli. Okay, and Nikuli actually said that okay, so there exists a lattice. Okay, so a zeta module of finite rank. Moreover, the rank is 16. Okay, and it's negative defined. So negative means that the product by the each element here, when you consider is 1, is negative. Okay, and he said that okay, if my K3 surface is a Kummer, so comes from the minimal resolution of this quotient by a torus and the natural involution, then there always exists a lattice that actually contains these 16 exceptional curves. So do you remember that each fixed element in A was a singularity in the quotient of type A1, and then when I resolve it, I get a -2 curve. Okay, so now he saw actually that that it's more small, so it's something that in technical words is the minimal primitive sublattice, and it's in the cohomology of my Kummer, and contain also the whole collections by these -2 curves, plus something else that is something in a linear combination of these exceptional curves, but maybe you have to taken with coefficients in Q. So it's something that actually comes from the discriminant group. That one. So this is the first criteria, and then he said, okay, and then he characterized properly when a K3 surface is the Kummer surface. So he said that that happens. So now I have to restrict into the Neron severity that counts my curves. And then if I found a lattice like K, okay, an abstract lattice with this information in a primitive way in the Neron severity of X, then then you can find an abelian torus, and so that this K3 surface is the isomorphic to the minimal resolution of the torus by the involution. So this is at the level of lattices. So that's what is powerful, this technique also. So then if you see what happened with the Picard number of this Kummer, we saw that actually have to be greater or equal than 16, right? So this is something that so if you want to expect in something like that, the rank of your K3 surfaces actually have to be greater or equal than 16. And then the cases are 16, non-projected case, so 17, 18, 19, and 20. And the first one who answered a question that always happened, it was given by Chioda and Inos, and they proved that if your K3 surfaces have the top Picard number, then always exists an involution on your K3 surfaces, a particular involution, so that the quotient is birational to the Kummer of some two-dimensional complex torus. So why a particular involution? Because this involution actually is something that preserves the period. And this is the role of the symplectic automorphism here. So later, okay, Morrison, where actually he complete the answer for the whole algebraic K3 surfaces. So now the Picard number have to be greater or equal than 17, and he characterized when that happens in terms of the transcendental lattices. I don't present the characterization here, but I just mentioned that there exists, and they are very precise. All right. So what is now so how can relate both models? So the idea is to introduce. So Morrison do this definition. So he was interested to say, okay, when my K3 surface admit this involution in order to get that the quotient is isomorphic. I mean, when I resolve the quotient is also isomorphic to the minimal resolution on the torus and the natural involution. So this actually it's something that we can summarize in this kind of diagrams, and then we ask him for basically the existence of this involution here in at the level of my K3 surface and this quotient here. And since we mentioned that we want that the transcendental of the Kummer is actually isomorphic to 2 times of the transcendental of A, then at the level of X and A, the input, we ask actually that there exists an hot isometry between the transcendental of A and my K3 surfaces. So this is the conditions of that a K3 surface admit a Schrödinger structure. So now I have here an involution that acts in cohomology. So you have an involution of X. You take the pullback in cohomology, and then you extend this pullback with coefficients in C. And if you consider the hot structure of your K3 surfaces, you ask that the symplectic automorphisms respect to the holomorphic two forms, the action is the identity. Okay, so basically that they say that symplectic automorphisms preserve the period. And then if you ask what you want, that the minimal resolution of the quotient coincide with the Kummer or some of torus. So this is the definition. And later Morrison say, okay, uh, in order to characterize these K3 surfaces admitting these geodynamic structures, let's say that we have to study the induced mapping homology, uh, and let's see what happened at the level of the neuron severity. Okay, so these K3 surfaces have a large neuron severity because, in particular, I mean, have something of rank 16, right, at least. So this is the role of the how to get the decomposition of the homology group. And if you remember that for any K3 surfaces, you can decompose like the 3 copies of U plus 2 copies of E8. So, well, in the case of involutions, uh, the symplectic involution actually respect this splitting. Okay, and when your K3 surfaces admit this kind of structures, so Schrödinger's structure, that means that in the 2 copies of E8, they are interchanged. Okay, and so you have an embedding primitive of these 2 copies of E8 in the neuron severity of your K3 surfaces, and moreover they interchange. So there is a permutation of these two copies of E8. So he also said that, okay, that happens also as equivalent that your transcendental, it's into the 3 copies of U, just because the transcendental is the orthogonal complement of the neuron severity in the homology. And then, of course, you ask that the isometry of at the level of hot structure. So also Tx is isometric to Ta. Okay, so what happened in general? So we would like to say, okay, maybe I don't know, maybe we can also construct a classic not classic Kummer surfaces, like I take a torus, and my torus comes free with this involution, so that I can consider the closure and blah blah blah. No, now I want to ask, if I consider my torus, okay, and if I consider a symplectic automorphism on my torus, what happens if I consider the quotient? Okay, so this is, of course, this notion is valid when your automorphism is of finite order. And then if you, again, the same game, so you consider the fixed locus of sigma, you consider I mean, you look that there are isolated points, and then you see what are the corresponding singularity in the quotient. And so each fixed point induce a singular point in the quotient, and actually have ADE type of singularities. Okay, and then if you are lucky, you say, okay, more of the time you are lucky because they are not so worst. And then you consider the minimal resolution of these singularities. Okay, and then you see what is the cum generalized of this A. Okay, so just the minimal resolution of this one. Okay, and then you have some, so this is the diagram that I designed it before, and as I mentioned, this is new surfaces, but with isolated singularities of AD type, and the minimal desingularization of this is actually sorry. So this is now in the context of a K3 surfaces. So now X is, it's my so this picture here, sorry, that I designed here, was in terms of my torus. Okay, and now I want to construct this something like a new K3 surface is given by the minimal resolution of this quotient. But now this one is actually in terms of K3 surfaces. So this one is a K3 surface here. Then I consider a symplectic automorphism. So the pullback in the period is the identity. So I preserve it. This is very important in order to get a K3 surfaces. And then I do the same. So I consider the fixed locus of sigma. Then I consider the singularities here. and then I resolve the singularities. And in my new model, I have a set of minus two curves with some particular configuration. The particular configuration depends on the singularity that I have in the quotient. And the type of the singularities actually depends only on the order of the automorphism. So why it's again an K3 surfaces, since the automorphism is symplectic. So in particular, this beta is actually an Akrepan resolution, okay? And then as again, I get that the quotient is a normal. I get this type of singularities. I get that the y is now a K3 surface, and now I have a connection between my first K3 surface is x and the second one, which is y, by a generically finite map of degree, the order of the automorphism. Okay, so this is also useful in order to understand, for example, moduli spaces of K3 surfaces. I mean, the relation between the moduli space of K3 surfaces admitting a symplectic automorphism and the moduli space of K3 surfaces that comes from minimal resolutions of quotient by K3 surfaces and symplectic ones. So this pi actually it's a good connection between these two families. Okay, and it's generically, of course, because we have that pi is the composition of q by beta minus 1. Okay, so the story say that how do you see this geometrical picture? So you can also do it at the level of local coordinates. So this is actually the first part is something that comes from the Cartan geometry. So this is something that if you consider a symplectic automorphism, you can find a holomorphic coordinate system where locally this map looks like this. So you take the first component and then you act by the inner root of the unity. Okay, and the second one is as it is written there is by the inverse. Okay, in the second component. And this is, if you see, this is the local information is something that just depends of the order of sigma. So Mukai actually say that, okay, this number it is finite, is bounded, and is bounded by 8. Okay, and these are the possibilities. So in particular, this number of as I mentioned before, the fixed locus of sigma depends just of the n. And for the case of an involution, you have that actually you get 8 singularities of A1 type. In the case of a symplectic automorphism of order 3, you get 6 fixed points, so 6 singular points in the quotient of type A2, actually. And then you resolve these singularities, and then you have to introduce some Dinkin diagrams as A2. And if you go in the other cases, then you have to consider, for example, in the non-prime case, more configurations, because there are also D type or E type, etc. So in the primes cases, you get always A n minus 1 type of singularity. But the other cases, you can also get D4, D2, or different singularities on the classification. And this is another important invariant at the level of the geometry of your K3 surfaces, and basically say that if your K3 surfaces admit this kind of automorphism, the Picard number has to be greater or equal than, in the case of the involution, to 8, or in the case of the three symplectic automorphisms, 12, and blah blah blah. So this is, for example, 8 in the non-projective case. If you consider the projective case, then you have to add the polarization, and then you get 9, 13, and so on. So let me show an example for a symplectic automorphism of order 3. So a K3 surfaces that you can obtain it as again, but the for the game of my torus, but now the torus admitting a symplectic automorphism of order 3, and also obtain it by some quotient in the K3 surfaces with a symplectic automorphism, but in the K3. And this is a picture that now involve elliptic fibrations. And basically, because if you consider an elliptic curve, so E here is an elliptic curve uh, with an automorphism of order 3. Okay, so I have a complex multiplication by 3. And then if you consider the times of E, the same elliptic curves, you can actually prove that they comes with a automorphism of order 3, and you add with the first coordinate by this automorphism and the second one by just the power of 2 of these elliptic automorphisms, you get something of order 3 in the product. So in my torus. And then if I consider the equation, I will get now 3 per time, 9 singular points, which I resolved and by beta. And then I get now here a K3 surface. Okay. So actually, if you put in this way, is something that you want to get that again this automorphism preserve the period. So since now the canonical line bundle also of this torus is trivial, now with following this diagram you get also that it's trivial for X, because this one is symplectic. I don't know what it did. Okay, and then and now if you take the projection of some elliptic curves, then doing the right quotient, then you get, for example, that this one, the composition of these two maps, actually give you an elliptic fibration for this X. Okay, so my new K3 surfaces comes with this geometrical picture with an elliptic fibration. Okay, and moreover, this elliptic fibration have this configuration. So let me do zoom. Okay, so what do you see here? So what is it? So here you see a lot of -2 curves. And also you have something nice, which are these sections, okay, in the Mordor-Weil group on your elliptic surfaces. And this is fundamental to define the automorphism on my K3 surface. So this is the configuration on my K3 surface X, okay? And then since I have a natural map here, which is given by the translation, for example, of one of these two torsion sections, you get an automorphism of order 3 on X, which is given by take O plus T1, then you get T1, because this one is the 0 section, and then T1 plus T1 is T2, and T2 plus T1 comes to 0. So this rule, this way they have to move these curves, actually give you something similar that I get for the case of the involution, where do you wanting to interchange these two copies of E8. But the problem is that if you want to see the pullback in homology of, for example, of this symplectic automorphism of order 3, you don't have that respect this splitting. Okay, and if you want to see something that interchanges 3 copies of something, this something will be a lattice, E6 lattice. You actually have to ask that the passing for zone isometry on my homology group, so the cohomology of a K3 surfaces, I can get this a way to how to write the cohomology of a K3 surfaces now in terms of something that contains these 3 copies of E6. And basically the picture, this picture also show you. So first is show you the 3 singular fibers in the elliptic vibration, which is this one and this second one. Okay, and sorry for the so this also, let me see. So yes, you saw what are the so let me just yeah, I don't know why it doesn't work, but okay, you understand what I'm trying to say. So this is the on a singular fiber on my elliptic vibration. This is P1. I have these 3 singular, these 3 particular points, and the in my vibration here uh, is admits 3 singular fibers of type this one for asterisk, and then you can if you included these torsions, these sections, then you get actually that there exists 3 copies of E6 that I hope don't, yes, do in a good way. Okay, I think is this one. I did it well. Oh fuck. Okay, there is something similar. So you can find a copy here of E6, okay, and the same plane and the same gain of the symplectic automorphism. Now we saw that the automorphism is a translation by T1, for example. Then he moved these copies of E6 in the second one, and also I get this permutation. Okay, so this is more or less the behavior or something that for order 3. And then we can also ask for a kind of generalized show diagnosis structures. But now just let me say that this is in order 3. Okay, and then again, as before, we have this kind of diagrams. So we want some also again that the transcendental of X is isomorphic to the transcendental of A. Okay, so respect that this is hot isometry, and also that I can get the model of my generalized Kummer for something that depends of this automorphism. So now this automorphism is symplectic for X, and it's also symplectic here for my torus. So, but there is something that is not free here, and is that the torus not always admit an asymplectic automorphism of order 3. And basically, who try to answer when a torus admit this kind of automorphism, he actually was given by Fujigi, and he did actually for several options or several orders, and then but just following this example, he actually say that that happens if and only if the transcendental of my torus can be embedded in a copy of U plus A2 minus 1. Okay, primitive, in a primitive way. So if we consider again the minimal primitive sublattice in the Neron severity of the Kummer, okay, so my generalized Kummer now, that contains these curves induced by resolve the quotient, then Bertini and Bart actually say that a K3 surfaces can be birational to the quotient of these torus with the symplectic automorphism of order 3 in a torus, if and only if you can find this abstract lattice in the Nenderer severity of my K3 surfaces. The K3 surfaces that are asked it admit or not these generalized ischiodiagnosis structures. And later, in collaboration with Alice Garbagnati, we actually prove that we can, this is, as I mentioned before, these two families can be are in relations. And then we can also characterize all of these K3 surfaces admitting three symplectic automorphisms, such that are birational to this quotient of a torus and a symplectic automorphism, but in the torus, if and only if we saw this behavior of we can find three copies of E6 in the neuron severity that are permutated as in the involution, but now something, a permutation of order 3. Okay, so here, these three copies of E6 change in this way. Okay, and this is how, for example, we can characterize this generalized diagnosis structure, but of order 3. So the other cases, I don't know, actually, I mean, there are some results in terms of the existence of these symplectic automorphisms for the Tori, and also there are results of the existence of these symplectic automorphisms for the K3 surfaces, but the way how to relate both in a kind of these diagrams is something that actually it's not known for other orders. So it's something that is known for involutions and now for order 3. So the last part actually is something that I start to formulate in these days, because I mean, there are many of these properties you can also get it for higher dimensional K3 surfaces. But the diagrams here are not so immediately, I mean, doesn't have these immediately construction. So as for other kind of singularities, then you just to take in consideration, I don't know, a product of K3 surfaces, and then you consider symplectic automorphisms for this product, then you have to see what are the locus, and then and how you can resolve it. And basically, there are notions here that I start to solve that it's in terms, for example, of K3 two types and the generalizers of Kummers. So there is something that that we can say at least for this kind of hyperkähler manifolds or irreducible holomorphic symplectic manifolds of K32 type. So let me just remind what is this. So basically, on a hyperkähler here of this type, it's something that you can get as a deformation equivalent of the Hilbert skin of 2 points on a K3 surface. And if you see, you have a lot of ingredients for as in the K3 surfaces. So you have also an lattice here that actually you can prove that for any hyperkähler manifold of K3 any type, you can get that this cohomology is isomorphic to the cohomology of a K3 surfaces plus something given by in the Hilbert scheme, since this is something that you can also get at the topological way. So if you consider the Hilbert scheme of endpoints, then you resolve the locus, and then you get an exceptional divisor here. So this is the part that corresponds to the Hilbert scheme of the exceptional divisor. And then if you want to do the same role, you can also apply the lattice theory but now for this group of cohomology. Okay, and now the crab product is actually, you can also pass for this abstract lattice in order to say, for example, when the hyperkähler manifold of K3n type admitting these involutions. Okay, so these symplectic involutions, or now symplectic automorphisms of finite order, and then the story is more or less the same. But and in parallel, you can also get similar constructions in terms of the Tori. In those part, actually, it's concerning to the generalized Kummer. So this is something that if you want to give if you want to relate or again to get these geometrical examples, but now in these hypercolor manifolds, then you also have to do in the at the level of lattices and ask how can I relate both of these families. Okay, and this is also something that it's possible to do. I think that there are many resources according to the existence of these symplectic automorphisms in both sides, and and then there are many results on Mogardi, on Chiara Camera about Nicolin, sorry, about involutions. And the extra ingredient here is that you can also can relate it some orbifolds, which are given by partial resolution of these quotients. Okay, so on the K3 surfaces, we get it that this again on a K3 surfaces. In the case of a higher dimensional, you don't get immediately on a hyperkähler manifold. You don't get something smooth. You get actually something that is an orbifold, and then you want to try to do the theory, but now for these generalizations of smooth hypercolor manifolds. So this is more or less the motivation, how to connect. I mean, I presented here for K3 surfaces, but then the natural question is what happened for the product of two K3 surfaces? This is, if you do something good, you can get again on a hypercolor manifold here. And then let's see what happened in the quotient and how do you resolve these singularities. But of course, there are no so classification, immediately classifications as the ADE type. And I think that that's all. I mean, thank you very much.
Okay, Yulieth, thanks for your great talk. And so let's thank the speaker, please, for this great talk.